Welcome back to Appins of Code 2019. We're up to day 24, Christmas Eve. So what do you think? Christmas Eve, will that be a hard one? An easy one? All I know is day 25 is usually just a part 1. Doesn't really say whether it's hard or easy, it's just usually just one part. But day 24 could be a hard one. Don't really remember previous years. Only 2 more months till 2019 is done. That's correct, DOJ. And then I only have 2021 to go. If I can do that this year, well, yeah, this time I can do that this year. Then I'll be a holder of the much coveted 450 stars. Yay. Yeah, just open the IDE. Okay. 24. And then I won't have any other fight of this nature to code in the year. I'll have to find something else to do. Alright, Planet of Discord. You land on Eris. What's Eris? This is actually a planet. Dwarf, it's a dwarf planet. It's the 9th most massive known object orbiting the sun. It's greater mass, but smaller volume than Pluto. I never heard of Eris. I haven't really kept up with astronomy, but... So it was the 10th planet. It was considered to be the 10th planet, but now what's the definition? I can't keep up. Is it just Mercury, Venus, Earth, Jupiter, Saturn, Uranus, Neptune? I think so. Anyway, definition doesn't matter right now. As soon as you do, your sensors start picking up strange life forms are moving around. Eris is infested with bugs. Well, that's cool if it has life, at least. 2021, just all ink code. Somehow I don't think he did the ink code thing again. Although he did do assembly programs again. And some of them were actually individually harder than the ink code stuff, but I don't think he's done something of that nature where you build a program continuously, well, for more than like 2 or 3 problems. With an over 24-hour road trip for messages between you and Earth, you'll have to deal with this problem on your own. Eris isn't a very large place. A scan of the entire area fits into a 5x5 grid. So that's Eris. That's the whole planet. Okay. The scan shows bugs and empty spaces. Yeah, this is definitely a game of life type thing. Each minute, the bugs live and die based on the number of bugs in the 4 adjacent tiles. Excuse me, I need my coffee. Well, I opened the wrong packet and I poured creamer into my hot water first, so now I've got creamer. I don't even know what creamer is. Is it just like a powdered milk? Doesn't taste like it. It's cream, but in a powder form. It doesn't even taste like cream. It's just made the coffee a bit more rust colored. It's alright, I guess, but I prefer my coffees just plain black. A bug dies unless there is exactly one bug adjacent to it. It's mostly used to take the bitter out of coffee. I see. I think I like the bitter. That's one thing they don't like in Asia. Bitterness. It's the same with the beers, the coffees, everything. But in England, bitter is quite popular. People, especially in pubs, people really like their beers to be really bitter. Bug dies unless there is exactly one bug adjacent to it. An empty space becomes infested with a bug if exactly one or two bugs are adjacent to it. What are the actual Game of Life rules? Is this... Yeah, John Conway's Game of Life. Any live cell with fewer than 2 live neighbors dies. Not quite the same. So Conway's rules were more complex. Okay, but I mean, we'll see what happens when you tweak the rules a bit, so... The whole England conquered the world for spice and refuses to use any of it. I do prefer the Indian teas though, the ones with the like the stronger spices in them. Okay, so otherwise a bug or empty space remains the same. Okay. These rules are simpler than John Conway's Game of Life. We need to flip the board. So first you compute what's going to happen to each cell. Compute the new board, and then flip it in one atomic operation. Okay, fine. Yeah. To understand the nature of the bugs, watch for the first time a layout of bugs and empty spaces matches any previous layout. Alright. I don't think there's anything clever to this. I think you just run it until you see the same thing twice. To calculate the biodiversity rating for this layout, consider each tile left to right in the top row, left to right, and so on. Each of these powers of 2. Well, that's good for Python. Because those numbers are going to get quite big. But Python, you can have unlimited size on your numbers. Okay, so... I think part 1 is just simulate it and run it. I don't think there's any way you can cut corners here. Like, that's kind of the point of game of life. It's you create unpredictable chaos out of simple rules, and you can't predict what will happen in 1,000 moves without simulating it. Sort of. Okay. Let's copy in the input there. For line. Oh no, don't change day 23. Okay. Just copy this line here. For line in read lines. So I want to say grid equals copy and paste. Yeah, it is a very important tool. I should map it to like the buttons on the sides of my mouse. But I'm just so used to doing Control-C, Control-V that I'll just keep doing that anyway, even if I map it. Grid equals... Just we'll make it as a two-dimensional list. So grid.append list line.strip. Strip off the new line characters. Put it in as a list. Okay. Okay, let's define a few useful methods here. Let's do pretty print. Grid for line in G. Print it all joined up. Join. And then, I don't know, print an empty line. How do you print an empty line? Just do that. Let's test this out. Pretty print the original grid. Yeah, okay. So I think we'll want to have a method which defines a signature, a unique signature for a grid, and that's really just going to be the full string as a string, because that's hashable. So let's call it sig g. Returns, it's going to be join line or line in G. So we join up the individual lines and then join them all up as one big string. So let's check this. It should be one long string now. Well, not like that. Oh, whoops. I've done pretty print. No. Print. Okay, there we go. Okay, everything seems in order. So What was it that we wanted to do? We want to just keep running it until we see the first layout that appears in our pretty print. Yeah, that's a term that, well, I don't see it being used that often now, but it used to be. It might still be a term that's used for describing a print when you a print method which does a bit of enhancing or modification to make something easier to read by a human rather than printing it explicitly. So like adding lines as separators and stuff like that. It's a bit confusing because it looks like a typo. Well, normally you would just write pretty print, I guess. So let's just say visited equals just the signature of this original grid. Put it in a set. So this is all the visited grids. So now we just do like while true. We can do another method here. Define get next. So this gets the next grid. What's the... N equals length of grid. M equals length of grid. 0. It's a square grid, I suppose, but we can just treat it as a rectangle anyway. I think we need a get neighbors method. We always need a get neighbors method. Define get neighbors. 2 usages. Oh, whoops. Get neighbors for a given I and j. So for delta in, so we go 1, 0, minus 1, 0, 0, 1, 0, minus 1. Neighbor I, neighbor j equals I plus delta j plus delta 1 if 0 is less or equal to neighbor I is less than n and 0 is less than or equal to neighbor j is less than m. Yield we need to supply a grid as well. Yield G, neighbor I, neighbor J. So this is getting the up, left, down, and right neighbors, but omitting them if they're off the side of the grid. Okay. what we're actually trying to compute though is how many bugs there are. So I don't think we'll need get neighbors. We could just say num bug neighbors. Or, I don't know, num adjacent bugs. Result. Hang on. Result plus equal. So we add one if this is a bug, which is what, hash? Turn results. That gets the number of adjacent bugs. So to get the next grid, new grid, create a new grid for row in G. New row equals hang on. For I in range N or J in range M. Create a new empty row to add to this new grid. For each character in the original row, we look at how many bugs are adjacent to it, so we can say so if there's a bug, and there is not exactly one bug next to it, then it dies. Alright, that's the first rule. So if G I J is hash and num adjacent bugs I J G is not exactly 1, then we append an empty space, which is dot. The other condition, an empty space becomes a bug if 1 or 2 bugs are adjacent to it. So if it's an empty space and the number of adjacent bugs is between 1 and 2, let me append a bug. Else we just add whatever it was, but stays the same as whatever it was before. So Um, after this row, we just put new grid dot append new row. Okay. Probably would have been better if I just initialized. That's fine. So at the end of this, we'll have a new grid. In the same format. Just return it then. So while true, grid equals next. Get next. Grid. If the signature of this new grid is in visited, we'll break out of this loop. Otherwise, put it in. So if we get this far, we will see a grid that we've seen before. So let's pretty print it. Was that different to the original grid? Yes, it is. So that seems to be... Okay, that's a revisited state. It's symmetric. That's interesting. Diagonally symmetric. No, it's not. It's not symmetric. Okay, what do we want to do now? To calculate the biodiversity rating for this layout, go from left to right, from top to bottom, increasing powers of 2. Okay. Biodiversity equals 0 for I in range N, for J in range M, if grid IJ is a hash, we add uh 2 to the power of it's going to be n time m times I plus j. Print biodiversity 184. Correct. All right. I mean, it's hard to get that wrong because if you find a grid that's visited before, it's gonna match something in your visited set. So, well, I suppose if you did the rules differently, you might end up at a different repeated state. So that means it cycles, because if we visited a state it's been in before, it will just keep cycling through those states, won't it? After careful analysis, one thing is certain: you have no idea where all these bugs are coming from. Then you remember, Eris is an old Plutonian settlement. Clearly the bugs are coming from recursively folded space. Uh-oh. They use the R word. Recursively. But is this... Looks like this recursive might just be depth again, like we had before. This 5x5 grid is only one level in an infinite number of recursion levels. The tile in the middle of the grid is actually another 5x5 grid. The grid in your scan is contained as the middle tile of a larger 5x5 grid, and so on. The two levels of grids look like this. Okay. Really like infinity problems. So the scan you took shows where the bugs are on a single level of this structure. The middle tile of your scan is empty to accommodate the recursive grids within it. Initially, no other levels contain bugs. So we're seeing, for all intents and purposes, the 0 level. So it's recursive both ways. We're not at the top. There's also... Oh yeah, it is. It's recursive both ways. Wow, okay. Tiles still count as adjacent if they are directly up, down, left, or right of a given tile. Some tiles have adjacent tiles at a recursion level above or below its own level. Tile 19 has 4 adjacent tiles. 14, 18, 20, and 24. So 19 is regular. Tile G has 4 adjacent tiles. B, F, H, and L. Okay, that's normal. Tile D, this one, has 4 adjacent tiles. 8. C, E, and I. E. Alright, I get it. 8, 14, D, and J. Tile 14 has 8 adjacent tiles, I see. So it's adjacent to E, J, O, T, Y, 15, 9, and 19. Okay. Seems like it got a bit more complicated, yeah. So after 10 minutes, for the example, this is what it would look like. 5, minus 5, minus 4, minus 3. Okay, I don't actually... So the important thing is everything not in our initial grid starts as empty. So this is a place for default dict to shine, because we can use default dict to default everything to empty until it becomes something otherwise. So we basically got 3 coordinates. We've got I for the row, J for the column, and let's say like D for the depth. Oh, and we're not looking for... We don't have to hash it anymore. We're not looking for a match. We're just simulating 200 steps. Okay. If I handle this adjacency thing correct, then this is not hard at all, is it? You just run it 200 times. And it's computationally not even that... It wouldn't take that many steps because, okay, the depth increases, but it's not like it's going up exponentially. What's... Is it exponential growth? I don't think so. Every step we could add a new depth. But we wouldn't add 2 more depths. We would only add, at most, 1 down and 1 up. So, at most, you're adding, like, 25 new cells each step, so that's not exponential, is it? Like, you can never add 2 levels of depth, well, more than 2 levels of depth in one step. I don't see how that could happen. So okay, we just need to code this adjacency thing. That's the confusing bit, but... Alright. But I don't think it's hard. So we do... Alright, so we don't want a grid the way we've done it anymore, or at least... we define the grid in a new way. We just want... default dicts. Let's say int. So it's going to be 0 if it's a space and 1 if it's a bug, and it will default to 0. So let's just fetch the input again, fresh input. So if each individual character will say if the character is a hash, we'll put, so the coordinates that we put in the grid, hang on, we don't need a default dict. We just need a set here. Just a set of bugs. That's all we need, isn't it? Yeah. if it's a hash, we put things in the set. So instead of calling it grid, let's say bugs equals set. So we'll put bugs.add the coordinates, which will be I, J, and 0 depth to begin with. And we ignore the center. That's like the next layer. Okay, so we've got a set of bugs and where all the bugs are in terms of I, J, and depth. Okay. So we need a... So the complicated bit is the get neighbors method, I suppose. So in one layer of... Oh! Okay, no. In one layer of depth, there are 25... or 24, actually, cells. Now... Are we gonna write 24 different things? Not well. There is symmetry here, but it's a bit. Alright, I see the pattern. So the special cases are if... Well, let me show the thing again. If it's on the top row, then the 8 becomes a neighbor of the upper layer. Negative, let's say the negative layer. Let's say positive, you go inner, and negative, you go outer. So if it's on the top row, you get that. If it's on the side, so we need to make these checks individually, then you get the position 15 of the outer layer. If it's, and the right column and the bottom row also. And then if it's 8, you need to add these 5. If it's 12, you need to add these A to U. If it's 18, you need to add these. So basically we need 1, 2, 3, 4, 5, 6, 7, 8 individual checks to make. And if those 8 if it's none of those 8 checks, that means it's 7, 9, 17, and 19, I guess. Okay. Alright, DJ. Good sleep. Don't think... Okay, once I get my head around this neighbors thing, I think the rest should be plain sailing. I don't see anything really too complicated after that. So it's just a case of writing out like 8 or 9 conditions. So let's try that. So we can reuse... Well, So for a given grid, for a given I, for a given j, for a given depth, we want to work out what the neighbors are, the adjacent neighbors of this cell. So we can reuse some of this logic just to get the neighbors within the same depth. So we could say the delta n so neighbor I equals neighbor j, blah blah blah. Now, if this neighbor is the center space, we want to discard it for now. Well, sort of. It's a question of which... Right, so the special cases are if neighbor I is negative, or if it's greater than n, neighbor j is negative or greater than n, or if neighbor I and neighbor j are 3, 3, n over 2, n over 2, basically. So just handle those separately, I suppose. So, if neighbor I is less than 0, that means our neighbor is off the grid upwards. So that means we add Alright, I didn't want to hard code the fact that it's 5 by 5, but I can't be bothered to make it generic now, so we'll just assume it's 5 by 5. So it is 5 by 5, so we can just say yield. So it's going to be 1, 2. So that's this row, this column. So that space there on the outer depth. So d minus 1. Okay. If neighbor I is greater or equal to n, alright, we know it's square, so let's just take that out. Yield. So in this one, it's on the bottom, so that means row 3, column 2. 3, 2, d minus 1. Elif neighbor J is less than 0. Yield. So this one, it's going to be row 2, column 1. Row 2, column 3. Alright. Elif. So if it's the center space, so neighbor I, neighbor J equals 2, 2. This is the tricky one because, alright, let's just leave this out for now. And in the last case, if it's none of the above, then yield the normal. Set at this layer of depth. So that gets all the neighbors. Oh. We don't need G in this, do we? This is just getting the neighbors as a set of coordinates. So, if it's the center cell, so in that case it matters whether we are above, left, down, or right. So... So if... Alright, so if we came from the left, in other words, we came from 2, 1, then we want to yield the whole left-hand column of the next layer of depth plus 1. So we do yield 0, 0, d plus 1, and then go downwards. Okay, we'll just do this. 0. I could do a 4. Okay, let's do 4. Row in range n. Yield row on column 0, d plus 1. Okay. Elif. So it's going to be similar. If we came from above, so we came from 1, 2. We want the whole top row. So for col in range n, we want row 0, col, d plus 1. Okay. Elif. So if we came from the right, so we came from 2, 3, I'm not sure if there's like a simpler way of putting this all together. Like there's definitely rotational symmetry, so I suppose you could do something with that. Rotate, do something 4 times, I don't know. So if we came from the right, we want the right-hand column. So we want row. So it'll be yield row 4. Otherwise, we would be in from the bottom. So it'll be call. We want the bottom. So we want the bottom row. So it'll be 4 call. All right, I think that's it. That should be the trickiest part of the whole thing. So for each of these 4 neighbors, we either yield 1 or 5 neighbors. But only one of them can be 5 at most. So we either altogether we yield 4 neighbors or 8 neighbors. Yeah. So that's get neighbors. So basically, so bugs is the set. We want to replace bugs with new bugs. So we want get new bugs for a given set of bugs. Now, we basically need to check every current bug and every cell next to a bug, because that could be affected. But nothing else. Nothing else could change from a bug to a non-bug or vice versa. So we need basically a queue, or just say cells to check equals a set, because we might end up putting a cell in there twice if there were bugs on either side. Or I, J, D in B. So for every current bug, we want to add that location, because we need to recheck it. It could not be, it could change to an empty space. And for neighbor in get neighbors, I, J, D. We want to check those as well. Let's add the neighbor. Okay, so now we've got a set of cells to check. We create a new bugs is a set for I, J, D in cells to check. So for a given spot to check, we have to follow the rules from before. So we have to say num adj bugs. Well, that's a method we had before. Num bugs equals 0. We want to count how many bugs are adjacent to it. So for neighbor in it's this again. If neighbor in B, that means that's a bug. So we could say num bugs plus equal neighbor in B. So we count how many bugs are next to it. And now we do these two rules from before. So we say what did we say before? This essentially. So if it was a bug, so if it was currently a bug and numbugs is not one, then new bugs add it is, what was the rule? It becomes an empty space. So we don't do anything. Pass. We don't add a new bug there. If it was an empty space, so if not in B and numbugs is between 1 and 2 inclusive, then it will be new bugs dot add IJD. Done a lot of typing of logic here. It's easy to slip up somewhere. Otherwise, we basically add it if and only if it was in B. So if in B, new bugs dot add that, right? And then return new bugs, I would hope. So those are the methods. Now what? What were we supposed to do? Do this 200 times. And then count how many bugs. That's just the size of this set. That's the beauty of this defaulting set. So for in range 200, bugs equals get new bugs of bugs. And then what? Just print length bugs. M. We're still using M. Okay. M. $1998. Correct. It sounds complicated, but it's like you don't. It's like the recursive thing we had before. Just don't think of it in terms of recursion. Just think of it in terms of Z levels. Z levels, like in a Dwarf Fortress-like game. But this one's a bit weirder because it's like a cone-shaped world. So as you go down, you have a bunch of neighbors. Well, it doesn't really have a topological equivalent. I don't know. That was a nice problem. That I didn't think... I mean, the key is really to just code the neighbor methods correctly. And I think this trick of using... storing a set of bugs. So when everything defaults to not bug, then you should only be recording the set of bugs. I've seen problems like these where people just record like 1,000 by 1,000 space, and then they try to record a 0 or a 1, depending on whether something's a bug or a not bug. But then they exceed the 1,000 by 1,000, so they say, oh, okay, I'll change the limit to 10,000. It's just more work, and you don't know ahead of time how many you'd need. But if you just store where the bugs are, that's usually the key to the game of life problems. You just store where the non-default things are, and whenever you check for a change, you restrict your set to all the existing bugs and their neighbors. Then you're efficiently storing the world, aren't you? You're just storing the new set of bugs, and you're not storing the gaps. You're not encoding the gaps, you're just encoding the bugs. Because it's the world basically has 0 density of bugs, like, in terms of, like, percentiles. If it became bug infested and there was more bugs than spaces, then you might want to record the spaces. Although in an infinite world, that would be... Well, you could have that situation. If they had it such that everywhere was bugs. No, because then they'd all die of a population immediately, but yeah. Okay. That was Christmas Eve. I thought that was easy. I'm curious what kind of times we'll see for this one. 42 minutes. Yeah, I think most of the time will be spent with the get neighbors. There's probably a clever way to speed that up, to code it faster. I can't think of what that would be. Like maybe rotate by 90 degrees 4 times, and so you do the logic for one rotation of it, and then do a for loop of... I don't know how to... That might actually be more work. I'm not sure. I think if you just encode it the way they phrased it, this maps to these, this maps to these maps to these, it doesn't take too long, but there could be a way to speed that up, but... Still, 42 minutes is... Yeah, I would say still a little bit on the long side. I don't know. I think I could have managed the top 100 here if I just kind of really rushed it. What about... Well, yeah. So tomorrow, well, day 25, which I might do tomorrow, will just be a part 1. Are we going to take a sneak peek of... I think we'll hold off on the sneak peek. We'll use the element of surprise for next time. One would expect it to be an int code, because it isn't odd numbered. So, probably will be, but we'll see. And the leaderboard. Almost there. Okay. So that, how long did that take me? 1 hour to get to the solution. Probably about 1 hour 5 minutes, 1 hour 10 minutes. 1 hour 5 minutes, I think. Okay, pretty good. Okay. See you next time. Bye-bye.